clear. I mean, I'm just a participant and don't have the share rights, so anything you will.
All right, well, we can start now. I guess it's 1 after the hour. Welcome everyone to TSV area at 110. I hope you're all having a good remote meeting. Approaching the end here, I think. This is the note well. I think probably most of you, if not all of you, have seen this. If you have any, if you need to read this detail, please type this into your IETF note well into your favorite search engine, and you can review it in detail, click the links, and find out everything you want to know about note well. This is the agenda for today. I would like to bash my own agenda and actually just move the open mic in front of Ed's DTN talk. Just because I think it'll be shorter, and I just want to give DTN the time it needs to take us where the discussion wants to go. So after the normal trivia and the open mic, we're going to have Edward Berine of the, I hope I pronounced that correctly, of the DTN working group. He's the new chair there, and he's going to, repeating the experience of our TAPS presentation last time, we're going to highlight another less known part of the area and talk about DTN, which is pretty cool. It's got lots of deep space stuff, which I think is cool. And it's also a lot of interesting and challenging technical problems. So looking forward to that talk. Would anyone else like to bash the agenda? Okay, our most significant change, I think, is that as of yesterday, in a somewhat bittersweet moment, we're not saying goodbye to Magnus by any means. He's not going anywhere, but he will no longer be one of the area directors. Magnus has done a total of 6 years of the job, beginning in 2006, and just concluded a 2-year term. It has been incredibly valuable to me to have someone with that depth of experience, both as an AD and as in the transport area and the IETF in general, because I'm not necessarily strong in that particular area, and just having his advice and his wisdom on a number of matters has been invaluable to me. So, and you know, I think he's done a lot of things for a lot of people in this area. His most notable achievement, probably, I think he would say his most notable achievement in this term was getting Quick out the door, just under the wire, which is, of course, an enormously consequential development, not just for the transport area, but for the internet. And of course, Zahed is moving into that position. He's taking all of the working groups that Magnus had, except we are switching TRAM and RMCAT for reasons that aren't worth explaining, and probably won't have any impact on anything, frankly, because those groups appear to be winding down. So Magnus, any words you would like to share with us?
Thank you very much for those words. Yeah, it's been 2 fairly interesting years, been intense with Quick, but I also would like to really, I think the large accomplishment has been to actually get the DTN core specs out. That, in some sense, has taken more work from me as an AD, and a lot of foreigner issues with cross-area relations, because DTN, as you will see, is actually not just the transfer protocol. It's the whole IETF squished into one working group in some sense for that particular problem. So it's a lot of challenging problems, and security, routing, etc. all exist in there, but we will learn more about that later. But so therefore, actually, it's happy that we managed to get the first set of specs as standards track out, and that the working group can continue to work. There's been a number of other specs, but actually, looking back, this 2-year term has been, from a document perspective, fairly light, and we haven't. I wish we maybe got more through in some sense, but yeah, still IETF changes, and that's been noticeable also compared to my 2006 to 2010 term. It's another ISD, it's another IETF. Logically, you maybe not notice it when you're just looking here, but when you take this managerial role up, you see a little bit more, and you actually see what has changed, etc. So I enjoy it, but I'm gonna enjoy being back, going back to doing maybe a little more technical work, and Also, the TSB art is not going to get rid of me because I'm back both reviewing and I'm going to probably work a little bit more intensely to assign them documents to help out Wes in the triage position. So, and I hope every one of you will be happy with Jed as a replacement. As we are colleagues and work fairly close, I will be able to assist him quite a lot. So, yeah, done.
Thanks, Magnus, for your work and your friendship. Zahed, would you like to introduce yourself?
Yes, I would. So thanks, Magnus and Martin Dick for having me here. I need to be here to some extent. So my name is Jahed Sharkar, but usually people call me short version of that, Jahed. So you can call me Jahed. So I work at Ericsson, particularly Ericsson Research, especially with Magnus as colleague for last 13 years. So we have been doing a lot of work internally in Ericsson Research together. And then I live in Stockholm, Sweden. So that's it. My entry in IETF is from 2008. After then, I have been working on different working groups. I think it was PCN working group. That's where I first posted my draft. And then I worked in VD Core, WebRTC, and more like Quick, and I have chaired tabs, ARMCAT, substantial work done in ARMCAT. So internally also, I have been working on different layers like application layer, transport layer, and radio layer. So I have some experience on the mobile networks. Obviously, I work for Ericsson. So that's it. That's who am I. As some of you might already know me. And I'm looking forward. I think I'm already getting, so two things I did. One, I get assured from Magnus, he's not abandoning me. And the other thing is like, I'm taking on some of the stack that he has left. So nice work done, great achievements, Magnus. Hopefully I live up to the expectation.
Welcome, Zahed. I'm looking forward to spending the next couple of years with you. This will be fun.
Yep.
Moving on. Here is a update of the working groups from across the area. I don't know if there's anything that my colleagues here would like to highlight in particular, but I'll just give you a moment to look through that. I will say that Alto DTN are rapidly approaching a recharter, as is Quick for that matter. And so if you're interested in the overall direction of those groups, this is a good time to get involved in those. And I just also note the 793 BIS, which is about as foundational as they come in terms of transport area documents, is in working group last call. So obviously not a giant change to the way TCP works, but something that most of us hold near and dear to our hearts. So Magnus, did we ship anything of consequence since 109? I can't remember. Like I think it's. I mean, it wasn't really much happening.
No, only 9 specifications. So that's new. And
well,
the fact that we actually, I mean, the first 4 of the quick documents, I do expect to within weeks, as I said yesterday in the plenary too. There's nothing preventing it. It's just the editing time from the RFC editor here, and then the Office 48, and there's no known issues before it's published. The quick HTTP and QPAC specs, they're gonna be stuck behind the misref in HBBIS, but I expect it to come out within a few months. They are making progress, and we're already working with Blast Call a few build back, so it's making progress. Yes.
So not only Quick and DTN, which we've already spoken about the significance of that, but also Cluster 238, the pile of RMCAT documents that was stuck forever, actually made it to RFC. So the queue is much smaller than it used to be. Just a few things that are blocked because of some down references, mainly from IPPM. So good work, everybody. It's been a very productive interim between IETF 109 and today. So nice work.
Yeah, and I expect there's a few more of those documents that was from 309 is actually going to start moving, aren't they? Some of the IPPM documents still, and I hope the NFS is not too far off either, but it's.
And there are 3 or 4 that are through IETF last call. They're just kind of dealing with some ISG issues and whatnot. So we're really turning the crank pretty well here as an area. This is our every meeting reminder that we have a TSV area review team, which greatly assists the ISG in reading documents from other areas and looking at them in transport lens and making sure they're not doing stupid stuff from a transport perspective. I invite you to contact Magnus or Wes. I think Magnus is not listed here, but I think as of today, he's back on the TSV art, or as of yesterday. So you can contact Wes or Magnus if you're interested in participating. I think it's a good opportunity to learn a little bit what's going on elsewhere in the IETF outside transport area, and also helps us a lot, helps create good quality documents. And I think, as you can see, that little number in parentheses is how many reviews they had to do since 109. So, people reading 1 or 2 documents, or in some cases 0 documents, and I would hope that shows that's not an incredibly onerous workload on people. So please, if this is something interests you, please contact either Wes or Magnus. And thanks to our reviewers for the good work that they've been doing.
Yep.
Okay, so that's, do I stop sharing? Okay. So that concludes the Administrivia, and I think we'll go ahead and open it up for open mic. If anyone has any concerns, issues, questions about things in the area of any 3 of us, this would be the time to get in the queue. Okay, there's a very content population out there. Either that or asleep, where most of us should be right now. Okay, so I think at this point we'll go ahead and hand off to Edward Barang, who is the DTN Working Group Chair, the newish one, and he is going to talk about this particular part of the area.
All right. So give me a moment as I figure out how to share my screen. Let's see.
There's a share button in the upper left. There's a monitor with a line through it. That's how you share your screen.
So I clicked share screen request, and I think I'm queued waiting to be given permission.
Oh, yes. Okay, yeah, the UI is a little backwards from my intuition. Okay, there we go. Now you're set.
All right. And are you seeing my screen? Oh, I'm seeing my screen. So. Okay. Hi, my name is Ed Barang. I'm from the Johns Hopkins University Applied Physics Laboratory. I'm a co-chair of the DTN Working Group, along with Rick Taylor from Airbus Defense and Space. I wanted to spend a little bit of time today and talk about just sort of the general area of delay-tolerant networking, and then some of the things that we're doing in the working group. And I see a couple of familiar names in the meeting, and some people who had been working on DTN in the past as well. So that's always good to see. Yes.
Can you go to full screen in your presentation?
Oh, certainly.
See if it works. I think it's going to be easy especially with your coming figures.
Oh, indeed.
Thank you.
So, no worries. So what I wanted to do was give just sort of an overview of the history of DTN, how we got here, how we came to understand the problems, how it came into IETF. And then in particular, as Magnus said before, DTN is a large and sort of cross-area set of concerns, but I wanted to then focus a little bit on how the bundle protocol, in particular the bundle protocol version 7, operates. It really is the transport protocol for DTN and the thing that has a lot of the attention, with the addition of how to secure that protocol. And then lastly, there are many case studies on the value of DTN in certain environments, and I picked one related to NASA optical communications. So if we talk a little bit about a brief history, we have some URLs in the top right here. If you go to nasa.gov, they have a couple of pages associated with why NASA cares about this. But as we sometimes like to say with DTN, it came from outer space. There was an initial desire to move from this very point-to-point link scenario, which is what we have for the most part now in deep space, where individual space agencies build their entire direct-to-Earth infrastructure when they land on Mars, when they start landing on the moon, when they start putting orbiters and other deep space assets into space. And how do we get to a point where we get to some sort of deeply, richly networked model of spacecraft? Could we get to a point where landers are only carrying enough radio to get up to an orbiter and can rely on a network to give them that multi-hop back? And in particular, with the nonlinearities of transmission, adding those hops where you can get to a more resource node actually can increase the data rates while reducing size, weight, and power on landers. And so there's really a significant desire to get to that point. So when space agencies in general and NASA in particular started looking through this, they said, well, there are a couple of do's and do nots that we think we need here. Certainly there were a few do nots, which are, we can't always assume that an end-to-end path exists all at once. If you're a lander and the orbiter isn't overhead, then you can't talk to it. If the orbiter is overhead, but you don't have line of sight back to Earth, you can't talk to ground. You therefore also, given long light round-trip delays and just generally the resource-constrained nature of some of these devices, you also don't always have the ability to keep end states at the lander, down to ground station, and so on. And certainly because of those first two things, if you do have to do retransmissions, you don't want to retransmit from the original message source, because it's hard enough to get through the network, and starting all over again from scratch makes that more difficult. You do want to store data, sometimes clearly for milliseconds, sometimes for days, depending on when you get passes and when you can get dishes on Earth to point to things. And because you might not have end state information at endpoints, session information at endpoints, you may want to increase the amount of annotative metadata that you take with you in your messages, either encoded in payloads, but from the networking layer also included as extra secondary headers in the message itself. And then came the question of, well, if we do that from a transport perspective, then how do we secure things? Now, obviously, we know we can't rely solely on physical layer security, but if you are in this sort of top picture of point-to-point links without really a networking model, there tends to be an over-reliance on that kind of security. If we have annotative metadata added as secondary headers in a packet, in a bundles, as we'll come to see, does that change how we secure things? And then how do we make sure that while we are storing things for milliseconds or days, that they are secured? And then there were other questions about how much autonomy goes into network management, and how do we do routing with time variant graphs, and so on. And when we started asking those kinds of questions, then the first thing you do is you say, well, what do we currently have, and what can we currently reuse? We certainly don't want to make a new thing just because. And there were sort of two driving concerns that came out of everything we just talked about. The first was delay, and the second was disruption. And the delay case is fairly clear. If we look at this particular illustration where we have some number of nodes 1, 2, 3, and 4 on the vertical, with some notion of time on the horizontal, and if blue here or the shaded area represents connectivity between the nodes, if you have a data volume, which we call D1, and it has to wait for an end-to-end node 1 to node 4 path to exist all at once, it may be waiting for a very long time, and it may be waiting for long enough that by the time that transmit opportunity comes, there's another data volume which would be in contention with that same end-to-end path. And if, of course, we can take advantage of sooner hops than waiting for an end-to-end path, then the ability to exfiltrate data off of a particular platform sooner, certainly for resource-constrained devices, allows you to get data off your platform so that you can free up storage and take new observations. But it also means these kinds of link opportunities don't become wasted in the network. The other observation was disruptions, and what happens when we have frequent enough disruptions that the disruptions are not considered strange cases to recover from, but they actually represent the normal operation of the network as you have it. So if we look at a standard session establishment ConOp, where we take some amount of time to synchronize on information, we do data exchange and keep sessions alive, we do some cleanup at the end. If there's negligible disruption, it's all handled as part of just the minor jitter in the network. If you get infrequent disruptions of significant length, this graphic isn't meant to imply that packets are actually exploding, but if we sort of lose and time out, we may have to reestablish sessions, or if the session itself collapses, we may have to reestablish sessions. And there's an implied focus here on if we can just wait out the storm, then we can go back to normal operations. Of course, if the disruptions are regular enough and infrequent and perhaps even unplanned, then it becomes a lot harder to do that. And so the overall area of DTN started as delay-tolerant networking. It sort of morphed into disruption-tolerant networking. And it again, was this migration from, what would a solar system internet or an interplanetary internet look like 30, 50 years into the future, and what can we do now just to get little bits of it? That concept doesn't look dramatically different than local sensor networks. So instead of an orbiter over a lander on a planetary surface, you may have a data mule, maybe a UAV or a car or a bus going by and collecting sensor nodes, and maybe you have a SATCOM backhaul or maybe something else. And so if the problems on the left are mostly delay, the problems on the right might actually be more disruption. So then, if we said that was some of the statement of problem, what could we start doing to solve all of this? So DTN started looking at a couple of things related to existing protocols. Can we pick up and reuse IP? About 15, I think at this point, 15 years ago, there was a lot of discussion of whether a NASA should be baselining IP for their deep space networking aspirations. They started looking at the kind of things that are just sort of generally considered useful on the internet today. A couple of them are here. I'm sure that the people in the audience know and can come up with many more suggestions than the couple of bullets here. But the idea of caching and pushing information and not relying on sessions if you don't have to, or not having to rely on nested sessions and things of that nature. But a lot of this came down to the observation, again, that we don't have infinite access to bandwidth. And as silly as that sounds, if you are wholly in control of the construction of your purpose-built network, then there is a sense that you can build it and resource it enough for the data that's coming through. Whether that actually tends to be true over the entire lifetime of the network, and whether that remains true as you try and federate other networks, that tends to be we need to think 10, 15 years into the future. So being able to go to missions and be able to go to those who build their own networks and say, you cannot just assume that you will solve these problems by having relatively infinite access to bandwidth. Even when you do, in the moment, you're going to have to prioritize. You're going to want to look at whether or not your protocols are making good use of of your bandwidth. When you federate, you're going to need to worry about untrusted infrastructure. So DTN came back as specific solutions to some of the problems. And if you look to the right here, again, you see another concept of how folks would measure what they would call the latency of an IP network, where latency here includes the wait for the end-to-end path, versus what folks would call the DTN latency, which is the time essentially to get data off the platform. Then when we started looking at not just waiting for the end-to-end path, but the asymmetry of the likely links, where you may have very, very small, for example, very small uplinks, but very large downlinks. Again, going back to the space cases where an orbiter may have a much larger dish, more power, and be able to send data down to a lander or back to Earth significantly faster than a lander could otherwise, upload it. There are, again, a couple of features that you need. You need to be able to send data without knowing if the end state destination is online or not. You don't want to start retransmissions back from the beginning, partially because of the disconnected nature of these networks, and partially because of the significant asymmetries of the uplinks. If you uplink something and it gets somewhere, that's great. You don't want to then take that precious low-rate uplink and use it for the retransmissions if you can avoid it. And again, we talked a little bit about this concept of bundling annotative data with your payloads. If you do that, then your endpoints perhaps don't need to remember very much session information or special states. And all of this sort of boils down into what started to look like familiar features in other areas like asynchronous text messaging or email. And the interesting observation from the DTN perspective is, how do we get that down into a package that is small and efficient enough that it can run on very resource-constrained devices? So what then came out of that was a description of DTN as a suite of protocols and applications. And this is what is considered right now to be sort of the core set of concerns that are being addressed. Now, the four major protocols that are on the right are just so happen to be the four documents, three of which have gone out for centers, I think, are waiting on a missing reference, and then a third related to security. And these are the bundle protocol, BP version 7, and that is the main transport protocol. That is the protocol that allows for these extension headers for carrying additional information and the behavior around store and forward operations. A security protocol for securing the bundle, in particular the ability to handle and secure payloads separately from some of these secondary headers. Some context, security context, to provide information around how that security information and the cryptographic materials therein should be handled. And then because BP is considered an overlay, how it maps to the underlays that are carrying it, and in particular, out of the working group, the first convergence layer is a TCP convergence layer. Certainly not to imply that in the space cases we're using TCP for communication, but there are plenty of terrestrial uses of DTN that care about disruption, but otherwise don't have long signal propagation delays. But then there are other things that are waiting and progressing, and those include work on quality of service, time variant graph routing. In particular, the CCSDS is working through something called schedule aware bundle routing, and there is additional work on what it means to do key management in these kinds of very disconnected networks, and a look at network management to include more deterministic autonomy in the system, which is the Asynchronous Management Protocol, or AMP. Things that are not particularly considered part of the ecosystem are higher level user applications, delay tolerant file transfer or messaging or that sort of thing. And then the underlying transport mechanisms beyond how we talk about them in the convergence layers are also things that aren't considered part of that suite. So we've talked quite a bit about the NASA and the space part of the problem. DTN has the focus on DTN included many different folks over time. my understanding of the history is it started with NASA's concerns about interplanetary networking. DARPA picked it up for several years and worried about what it means in highly disrupted environments. The CCSDS, the Consultative Committee for Space Data Systems, looked at and started doing some initial standardizations specific to space, and then it came into the IRTF and the IETF. A DTN research group was formed in 2002 that was chaired by Kevin Fall and Jorg Ott, and its initial charter, pulled from the initial charter, which you can see from IRTF.org, concluded DTNRG, was the observation that non-interactive asynchronous messaging was important, and not only is it important in these space cases, but there are lots of different networks where this would be useful. The DTNRG produced 14 RFCs. 4 that were notable, they were all notable, but 4 that were fundamental were a DTN architecture, RFC 4838, the bundle protocol version 6, an initial security protocol, and an initial TCP convergence layer. In 2014, after some experimental deployments and field tests and lessons learned, a working group was formed to standardize this, and that was at IETF 91. And the initial charter, large parts of the initial charter were to take this work from the IRTF and the lessons learned from field deployments, and then update these different documents. And so, update RFC 5050, which was bundle protocol version 6, update 6257, the security protocol, provide a convergence layer RFC update to TCP. And that's what we've done, and that's why they mentioned we're going into our rechartering discussions now. So the ones that are in the editor's queue, bundle protocol 7, security, and TCP/CL version 4, and then another that's in AD evaluation, which is a security context to work with the security protocol. So if we speak just a little bit about the bundle protocol, and the first question always is, where does it live? And sometimes the answer is wherever you would like it to live. And if you were to go out and pull images off the internet, as I did to create this slide, you'll see a couple of different versions of this. But generally, a bundle agent or a forwarder is something that lives in an overlaying and speaking through its convergence layers. The value of that, of course, is that a BP instance can go over different underlying networks. And so just like for internet transfers and what hopefully is a very familiar simplification of TCP/IP networking, where you don't need to, of course, terminate TCP at every node, and TCP talks end to end. If we put a bundle layer in place, the bundle layer has the ability to do some storage because it is a store and forward network, but also it can sit over various convergence layers to include the point where perhaps you move away from TCP and into something else for to bridge a TCP part of the network with a non-TCP part of the network. The bundle itself is considered a bundle of blocks. So everything is termed a block. There is a primary block, which of course is a primary header. There is a payload block, which is a payload. And then there are a series of extension blocks, and you can have sort of any number of those. The primary block has standard primary header things in it. It identifies the bundle and particular processing options. It says adds routing information here. That just means that it has sort of source and destination information in it, as well as something called report to address to send administrative or other statuses as you work your way through the network. These optional blocks, extension blocks, you can have 0 of them, you can have more. And they are what carries additional annotative data, either annotative data for the payload or annotative data for the network, like what was your previous hop. And then the payload, of course, is the payload, and payloads can be full payloads, or payloads can be marked as fragments of some prior payload. If we look at the extension block mechanism in BP, one of the things that's interesting about it, of course, is that you can define, and the protocol is structured to allow for the creation of new extension blocks over time, and also for nodes that are doing processing to read these extension blocks, do whatever processing is necessary, and maybe even write back or update those extension blocks or add new ones. So it is not necessarily the case that the originator of a bundle is the only bundle agent that would add an extension block. Obviously, I just mentioned before something called the prior hop block. That's something that's added by a prior hop. So you could accept a bundle in, look at the prior hop block that is there, remove it, add your own, and send it along the way. And again, this is part of getting to that operational concept of not relying on state existing end-to-end, but being able to update it in the network as you go. And that's essentially what we talk about here. The value, of course, is that if you're able to synchronize state end-to-end, and end-to-end could mean truly message end-to-end, or maybe source to some initial gateway or something else, then you can make your messages smaller and just simply refer to sessions as you or session state that's synchronized along the way. If you can't rely on this, then you need to carry all of that information with you. And I think that is probably one of sort of the key insights behind bundle protocol: the need to store the data, waiting for a time variant path, and this idea that you can't always rely on your endpoints to tell you what you need, and you can't always rely on your destination to know everything it needs to know to process you. From that perspective, again, we talked about primary blocks and payload blocks. What's interesting in BPv7 is that the primary block is immutable, so it can be signed by the bundle source, and it should remain unchanged through the network unless it is fragmented, in which case new bundle fragments are created. But that's not the original bundle; that's a fragment. And then the payload block, it's always the last block in a bundle. The original BP version 6 had some ideas of extension blocks before a payload and extension blocks after a payload to help with the understanding of very large bundles, but we didn't see the need to carry that forward in BP version 7. And then the extension blocks in general, which are the ones that live between the primary block and the payload block, have some standard information in them. What is the type? What is the unique identifier of the block if you have more than one block of the same type existing in a bundle? And then are there interesting processing options associated with those blocks? So for example, because extension block types can be added to over time, you may find that not every bundle agent in a network understands every block type. And so there are options here that say things like, if you understand this block type, process it. But if you don't understand this block type, just pass it along quietly. Or if you don't understand the block type, then that's a problem, and remove that block from the bundle before you pass it along. Or if you don't understand the block type, that's a big problem, and get rid of the entire bundle and process it no further, or perhaps hold it off to the side for forensic analysis. Within the BPv7 spec itself, we define a couple of blocks that are useful, that we think are generally useful and need to be supported. The three of them here, the previous hop block, the previous node block, which is the information associated with the last transmitter of the bundle. A bundle age block, which carries the sort of accumulating milliseconds from the time the bundle was created until it was last forwarded. This is particularly helpful for devices that themselves can keep relative time, but have difficulty keeping absolute time. And then for areas where hop count is still a very useful thing, even in a delay tolerant network to avoid routing loops and things like that, particularly in time variant graphs. Carrying hop counts and hop limits may also be necessary in the network. And then there's another set of specifications called the BPSec, or the Bundle Protocol Security Protocol, which uses 2 additional blocks to carry integrity and confidentiality information. And I'll talk about those a little more in just a moment, which is right now, because it's a little more about security. So when we then asked ourselves, if we don't necessarily have end-to-end session information, and we have this additional metadata, what do we do? There were a couple of design decisions associated with a security protocol specific to bundle protocol. The first was, if we're having different kinds of information in a bundle, then having block level granularity is going to become important, because now information that normally would be in different payloads is now in a single bundle, and we may have to treat that differently. Perhaps we want to sign an extension block with metadata, or sign the primary block but encrypt a payload. And those are two different things that may have to coexist in a single PDU. Separately, if we accept that different nodes in a network could add extension blocks as we go, like with the prior POP extension block, well, then the node that adds a block may have to secure that block, and that's different than the node that created the bundle itself. So there are different sources of security in a PDU. And then, of course, because of those first two things, you will have different security policies. If you have different security sources in the network, they will probably have different identifications. They might be using different cipher suites, or if they're using the same cipher suite, they will probably have different keys or other cryptographic material associated with those cipher suites. To that end, different cipher suites and sets of cryptographic materials are active in the system. And if you take all of those four things, you then need to come back and say there must exist some limitations and constraints on this, so that we can deterministically process all of this and not wonder about who did what in what order in ways that we can't back it out, and back it out in a forensically recreatable way. So to that end, the security protocol uses the extension mechanisms in BP for the security of information in BP. To that end, we define two extension blocks related to security: a block integrity block for integrity services, and a block confidentiality block for confidentiality services. Block integrity is defined here as essentially an integrity mechanism over plain text. If, for example, you're using signing as your integrity mechanism, then you can sign plain text and you can sign multiple blocks at once, and it can carry that along. And there are some constraints associated with not having circular references. If you use bibs and BCBs for your security, and bibs can target BCBs, which can target bibs, which can target BCBs, that's something you want to avoid. So we had to put some constraints there. And then a confidentiality block is defined as confidentiality on the plain text and integrity over the ciphertext. What that means is any cipher suite used for the application of confidentiality, it really must be an AEAD cipher suite. It needs to carry with it, additional authentication data, and to include being able to do things like cryptographically bind blocks into a bundle, so that, for example, you could include the primary block of the bundle as part of the authenticated data, along with the ciphertext that's created when you create, for example, a signature. If we then sort of look through the security considerations unique to DTNs, there are certainly a lot of them. Obviously, with any kind of store and forward network, there's a lot of concern about person in the middle attacks. Clearly eavesdropping and working on things out of band and offline. The concern, of course, when you have blocks that are added and removed from a bundle, you worry about modification and replay, and then anything that's time variant, there are concerns about topology attacks as well. So for those who are interested in this, there is a good security analysis of this in the BPSec document itself under security considerations, where we talk through what we can handle inside of the bundle itself, and then what can't be handled from a security perspective solely inside of the bundle and would need to be taken more out of band in the network, but not in a particular bundle itself. The last thing I wanted to mention on the security side is, when would you use the BPSec protocol? So it is not something that needs to be used all the time, and it depends, of course, on the security you're trying to create. So if you want security at rest, then having the security as part of the protocol data unit itself certainly helps with that. It is nice to say that some of the blocks inside of a bundle are themselves encrypted by the network, and if the network's going to store this persistently for hours and days, then that security persists, and you don't have to decrypt a bundle coming out of a secure tunnel, and then re-encrypt it for storing it locally, and then decrypt it off of the local drive and then re-encrypt it for pushing it down the next tunnel. So you can save some of that if you need that kind of security at rest. Interestingly, obviously, we think that applications will provide encrypted payloads when the applications feel that that is necessary, but then all of the additional extension blocks and other network information itself will need to be encrypted. And then, of course, the underlying convergence layers we also assume provide security, but since the convergence layers may change as the bundle works its way through the network, then then again, having security within the bundle itself is a useful thing. The other interesting observation is that there are probably some different ways of using this that may be interesting to certain security operational concepts. Namely, if you're trying to create secure tunnels in networks, but they may want to overlap, if you use security solely as encapsulating the entirety of a bundle in ways that don't secure extension blocks and payloads separately, then it's all or nothing for things that are in a tunnel. However, if you wanted, because you're carrying different information, to have, for example, integrity over a primary block from the beginning to an end of a transmission, end to end, perhaps confidentiality for some subset, some other kind of confidentiality for another subset of the network, this becomes impossible to do if everything is treated the same within the PDU. However, if you look at this block by block and not PDU by PDU, you can start getting that kind of behavior. Then the last thing is just, there are many studies on how store and forward in general and bundle protocol in particular is useful in challenged environments and how we get data through. Here's one from 2014 called the Lunar Laser Communication Demonstration that NASA had run, and it was just to show the value of optical communication and how we are proceeding at that time. While many of us probably understand the value of that, certainly the driving value here is EIRP. That a NASA 34-meter antenna using 20 kilowatts of power can get about 8.3 EIRP. A lunar laser comm terminal, which is about 10 centimeters, using about a half a watt of power, can get the same EIRP, and that's just really motivating. So there was a DTN demo that was done in this way. It was using DTN up to and through, so bent piping through the lunar link. I don't think that DTN was actually on the spacecraft itself, but it was providing the actual data of handling when that link went up and down. And one of the things that they found in particular was one of the limiters of getting the data through, particularly back to Earth or up to the spacecraft initially, was clouds. What they called the all-natural laser comm link limiter. And what they found was that DTN worked just as it was supposed to. When things were good, delivery went through just as expected. Bundles were sent, that's the blue. Bundles were received back again. When the link went down, then they didn't get any of the receptions. However, once the link started to come back up, the data started to trickle in. And what was nice about it is this essential recovery period here was not swamped with control information, trying to reestablish a sense of session, thereby losing the data opportunities to control information. A little bit of control could be in extension blocks, but then the rest was coming in as data. And they found that this period of recovery versus other things that they had experimented with got more of the user data down faster, increased their good put. And for those reasons, NASA came back and said, we really need this technology for any time we're doing these kinds of operations. And then essentially there were also things here where just from optical to RF rate buffering was considered valuable to them as well. So that was my last slide. It's a little bit about the history of DTN. It came from outer space, but it has application to any kind of disruption, certainly link disruption, but also sometimes prioritization and disruption around administrative boundaries. We've pushed out transport and security protocols. We're looking at other topics right now, and if you're interested, please come and see us in the working group.
Well, thanks, Edward. That was really interesting, and I think really cool. I mean, I'm like a kid when I hear about this deep space stuff. So if any of you are super energized now to go be a part of DTN, you have to wait about 3 hours. The third session today is DTN is having their meeting at IETF 110. Let's open up the queue for questions. Okay, I see a lot of positive comments in the jabber, but no one wants to come to the mic. So I have a question. Just because, like, you know, here at the AD level, we're working on creating a little more press about what Tsvarea is doing, and also because I'm personally interested. Like, what has, like, to what extent has this been deployed? Like, I mean, obviously V7 is pretty new. And you know, you just showed this demo here, but like, are any probes or anything that have gone out used this or an earlier version of DTN technology? So
yes and no. Next question. No. So the yes and no. The issue, particularly on the space side, is early in mission formulation. You really need to have the standards set, and so there is. We are quite and keenly aware of some of the pressure to make sure that Bundle Protocol version 7 is out and out in a timely fashion, because it is necessary to have that RFC so that it can be put into contracts and requirements for missions. And missions won't adopt it until. However, Bundle Protocol version 6, RFC 5050, for a similar reason, was taken and standardized by the CCSDS, the Consultative Committee for Space Data Systems, as a blue book. And once that happened, missions did adopt it. So NASA Goddard has a large mission, I think it's $1 billion mission, called PACE, Plankton Aerosol something. And it will be using Bundle Protocol version 6. And what's interesting there is, by using it on a spacecraft, and this is not necessarily for delay and disruption, but just efficiency. You can have a file system, and you can worry about writing to files and doing garbage collection in file systems and so on. Or if you know you're going to create persistent data, and you can put it in a bundle, and it only needs to be persisted so that it can be sent. You're not going to open it and do surgery on it and save it again. You don't need the complexity of a file system to do all of that. And so you can have a little more efficient processing if you have a bundle store instead of a file system. So I'm really anxious to see whether missions start seeing those kinds of benefits as they go through their deployments, but it will fly on PACE. We're also going to hear in the DTN working group about an ESA, European Space Agency, a project called OPSSAT, which will be flying both Bundle Protocol version 6 and Bundle Protocol version 7. And we also have several industry folks who have non-space case uses of DTN, although they keep some of that private until they're ready to, release their, products and results and so on.
That's cool. I would like to thank Ed also for this presentation, because taking on DTN, this was like really a crash course for me. I would really like it.
Our secret agenda was to just save Zahed a bunch of reading. I think we succeeded at that.
I think we should do this for other working groups as well. NFSD4, next up.
Okay, so I guess, well, so this was we asked for an hour session, we got 2 hours, so I guess a lot of you are going to have another hour and gather. We really hope that you have, again, thanks to Edward for this talk, which I found super interesting, even though I don't have to read all the DTN docs. I hope that the rest of your 110 is productive. We'll see you at 111, and hopefully, again, Zahid and I will be gathered out town a lot if you want to hit us up about any particular issues more privately. So have a good rest of your meeting, and see you in San Francisco with a little bit of hope.
Yes.
Bye, everyone.
Bye.
Bye-bye.